We are now in a position to have a greater understanding of the underlying reasons for why ions of a certain charge form and what the relationship is between the size of ions relative to their parent atoms. Earlier in this video series we learned that cations, which are positively charged ions, are formed from metals which tend to lose enough electrons to attain the same number and arrangement of electrons as the noble gas immediately preceding it on the periodic table. We further learnt that anions, which are negatively charged ions, are formed from nonmetals which tend to gain enough electrons to attain the same number and arrangement of electrons as the noble gas immediately following it on the periodic table. We can see why this is the case for cations by looking at this table, where we see that the removal of inner or core electrons from atoms costs large amounts of energy compared to the removal of valence electrons. We can therefore predict that the loss of electrons to form cations will only involve valence electrons, and that the number of electrons lost will be determined by the stability of the resulting electron configuration and the amount of energy that it costs to remove those electrons. So, for example, metals in group 1A, 2A and 3A will lose 1, 2 and 3 electrons respectively to achieve a noble gas configuration, and the energies required to do this are not too large. By the time we get to groups 4A, 5A, 6A, etc., we can see that the energies required to lose enough electrons to gain a noble gas configuration start to get prohibitively high, and we tend not to see cations formed from elements in these groups, and this explains why it is only metals that tend to form cations. So, in summary, for cations, loss of electrons to form cations will only involve valence electrons. The number of electrons lost will be determined by the stability of the resulting electron configuration. Noble gas electron configurations are very stable, and we know that because noble gases are non-reactive and form very few stable compounds, and so consequently elements tend to form ions that have full electron shells, and cations such as magnesium in particular will lose the required amount of electrons to gain that electron configuration of a noble gas. So for example, magnesium will lose 2 electrons because by losing 2 electrons it goes from a electron configuration that has the neon core and the 2 3s valence electrons to just losing those 2 electrons to have the neon core, which we know is a stable electron configuration. Now for anions, elements with high electron affinity are more likely to form stable anions, and the number of electrons gained by an atom will again depend on the stability of the resulting electron configuration, and again the formation of a noble gas configuration is favoured. So for sulfur it will gain 2 electrons because by gaining 2 it will be transformed from a valence shell electron configuration that has 6 electrons, 3s2, 3p4, to a valence shell electron configuration that has 8 electrons and 2 full subshells there, the neon core 3s2, 3p6, and we know that that electron configuration is actually the electron configuration for argon, which we know is stable. Now, while these general rules apply to many main group elements in the S and P blocks, it's more difficult to apply the general rules to elements in other parts of the periodic table, such as the D block. And aside from full electron shells or full subshells, stable electron configurations are also obtained with half-filled subshells, so that ions that result in half-filled subshells will also be stable, and this can be used as a guide to predicting which stable ions may form, particularly in this part of the periodic table. Another property that a consideration of electron configurations can explain is the relative size of ions. Now, cations are always smaller than the neutral atoms from which they are derived, and this is because removal of one or more valence electrons decreases electron-electron repulsion, and their outer orbitals can therefore shrink. Removal of all the valence electrons leaves the outer orbitals completely empty, and the size of the ion is therefore determined by the size of the core orbitals, which exists in a shell of a lower n value compared to the neutral atom and will therefore have a smaller size. In the case of anions, they are always larger than the neutral atoms from which they are derived, and this is because addition of electrons into the valence shell increase electron-electron repulsion, and this gives the electrons higher energy, which leads to an increase in the size of the outermost orbitals. So, in summary, cations are smaller than the parent atom, anions are larger than the parent atom, and this figure here shows the extent of the difference between the ions and the parent atoms for some common elements.